Hello. So last time we started talking about the Riemann integral. Okay, and what we did was we talked about the Riemann integral for bounded functions. On compact intervals. Okay, and we saw that there was an example, a simple example, perhaps in some ways too simple to be interesting, but nonetheless an example of a non-Riemann integrable function, which was a bounded function on a compact interval. And which was a limit of a sequence of Riemann integrable functions. And so the idea was that this illustrated some deficiencies in the Riemann integral that we're going to redress. But before we do that, we're going to finish the Riemann integral. And really what we're going to do is we're going to relax these conditions. And it's not because it's so much important to do that, but rather just it's useful to do that to contrast it with the things we're going to do later. Okay, so we will do that. And then we'll almost certainly get started on the vague measure. Okay. All right. So let's now we want to define the Riemann integral for possibly unbounded functions on possibly non-compact intervals. And I'm going to do this in a quick and dirty way. There's kind of better ways and more general ways to do this, but I'm going to do it in a way that has the benefit of sort of being very intuitive. And since we're not really super interested in the most powerful theory of the Riemann integral possible, will be sufficient for our purposes. Okay, so let's let I be an interval. Okay, and we want to consider Riemann integrability and Riemann integral for functions f defined on I. And I'm going to require for this construction I will make that f restricted to any compact subinterval of I be Riemann integrable, as we talked about last time. Okay. All right. And so, again, we're going to do this in kind of a quick and dirty way. And the way we're going to do this is we're going to do it kind of non-compact interval by non-compact interval. And I'm not going to do this for all the cases, maybe just a couple to illustrate. Okay. So let's maybe look at I to be an unbounded interval, but closed, like so. Okay. So then I define the integral from a to infinity, f of x dx to be so sorry, I should say here, the way we're going to do this construction is we're first going to consider non-negative valued functions, right? Because we don't want to here think about the kinds of complications that can arise when you have positive and negative parts of the function that cancel out in just the right way. So we'll have quite a lot more to say about this as time goes by, but for now, that's the assumption that I'm going to make, is that f is non-negative valued. Okay, so then we're going to say that f is Riemann integrable if the limit. Okay, so the limit is the one that I will write down right now. Exists. Okay. And so notice that this expression here is the Riemann integral of f on the compact interval from a to r, and my assumption is that makes sense, okay, because f is Riemann integrable on that compact interval, and so really the statement here is about the existence of this limit. Okay, and if this limit exists, then obviously then okay, so if the limit exists, then f is Riemann integrable, and it's Riemann integral. Integral is this limit. Okay. Okay, so another case that's illustrative is let's take maybe A, B. Okay, so bounded but not closed interval. So we're going to say in this case, and so f is Riemann integrable. If limit, and here we're going to go integral from a to b, x dx is going to be the limit as little r goes to 0. Sorry, not 0, but a, integral from r to b x dx, if that limit exists. And again, it's Riemann integral is the limit. Okay, and then a final case that we'll look at is a not closed, not bounded case. So maybe let's take this one. All right, and then we're going to say that f is Riemann integrable if the limits All right, so so I'm going to kind of take two limits, one corresponding to openness here and one corresponding to unboundedness there. Okay, so it's going to be the limit as r goes to 0, and here I'm going to integrate from r to some c. Okay, so I'm going to choose a c in here. Okay, f of x dx, and the other limit is the limit as big R goes to infinity, interval c to r x dx. If these limits exist, and it's Riemann integral is the sum of these limits. Okay, so there's a few unsatisfactory things about this definition, one of which is the introduction of this c. But you can show that the existence of these limits, if it exists for one c, it exists for all c, and the value of the integral is independent of c, et cetera, et cetera. Okay, and then other cases are similar. Other cases of intervals, non-compact intervals, are similar. Okay, so that's how we're going to define the Riemann integral for non-negative valued functions on non-compact intervals. Okay, now let's relax the assumption of non-negative. Okay, just an arbitrary real valued function. And what we're going to do then is we're going to break this down into two cases of non-negative functions in kind of the obvious way. Okay, so we're going to define two functions, one f plus and one f minus, and f plus will kind of be the positive part of the function, and f minus will be the negative part of the function. And so this is going to be the max of f of x and 0. Okay, so when f of x is negative, it takes the value 0, and in fact f of x is positive, it takes the value f of x. All right, and then f minus of x is going to be the max of minus f of x 0. Okay, so so here, when f is positive, then minus f is, if f of x is positive, then minus f of x is going to be negative. And so you're going to get minus the value of f of x at points where f of x is negative, and all the other points you're going to get 0. And so f minus of x is kind of minus the negative part of f. Okay, so f minus and f plus are both positive, is the point. Okay, then f is Riemann integrable if both f plus and f minus are Riemann integrable. As I've defined above, because they're both positive functions. And the Riemann integral of f is integral over I of x dx is integral over I f plus of x dx minus integral over I minus of x dx. Okay. All right. So in this way of defining the integral, and this definition of the integral is going to carry over to our new definition of the integral as well, the Lebesgue integral. There's a feature here that you should be aware of. Okay, so this notion of integrability corresponds to what you would call absolute integrability. Okay, and for absolute integrability, the property that it has is that f is integrable by definition if and only if its absolute value is integrable. Okay. Because if you just look at the way we've put this together, f is f plus minus f minus, but the absolute value of f is f plus plus f minus. Okay, now you can think of doing this in a different way. Okay, and the different way would be like this, that up here, where I first defined these various cases of the integral, I did make, and that's why I was careful to check myself, I did make the assumption that in these initial constructions, f was positive or not negative. Okay, but there's another way of doing this where I would be allowed to relax that. Okay, so how are these things different? Okay, so there is another definition of integral, which is conditional rather than absolute. Okay, and what distinguishes these things? So in this definition, we define, for example, so I'm not going to go through this in detail. The integral from a to infinity f of x dx to be the limit as r goes to infinity, integral from a to r f of x dx, without requiring f to be non-negative. Okay, and so these definitions differ. Okay, so for example, and this is an example which is going to be important for us. We have the function, which is sometimes called the sinc function. Okay, and the definition of the sinc function is that it's sine x over x. Okay, and so at 0, where there's a possible ambiguity, you take the limit as x goes to 0. This is well defined, and it's 1. So you take the value of the function to be 1 there. Okay, so what does you could define this on all of R. Okay, is conditionally integrable, but not absolutely integrable. Okay. So the idea is, oops, the F looks like this, the graph. Okay, so it's a sine function that sort of decays to 0, like 1 over x at infinity. Okay, so it sort of does something like this. Okay, and so the idea with this function is that if you take the limit as r goes to infinity, okay, and you need because I'm taking this function defined on all of r, the way that you do this is you do it just like you do here, is you break your limits in half. One going from 0 to r, and the other one going from 0 to, let's say, minus r, and you require that both of those limits exist independently. But the point is that the negative bits, the positive bits and the negative bits cancel each other out just in such a way that the conditional integral exists, okay? But if you were to take the absolute value of this function, which would look something like that, right? You don't get this cancellation between the negative part and the positive part, and each part, the positive part and negative part, turns out are not Riemann integrable because they don't get to rely on the cancellations of the other part. Okay, this is entirely analogous to sums. Okay, so the sum converges, okay, conditionally, okay, when what that means is that the limit as n goes to infinity, sum j equals 1 to n minus 1 to the j over j exists, okay, but does not converge absolutely. Okay, and that's because the limit as n goes to infinity diverges to infinity. Okay, and so the phenomenon that happens with this limit existing, but this limit not existing, is exactly analogous to what's happening with this function. You know, here the minus and the positive and negative parts of the terms in this sum cancel each other out exactly in such a way that this limit exists. And so note that little L1, so I put my one up here, of F, the set of sequences in little L1 is the set of absolutely convergent sum of sequences whose sum is absolutely convergent. And so it's a set of sequences whose sum is absolutely, not conditionally, convergent. Now, there's all kinds of reasons why you prefer absolutely convergent or absolutely integrable to conditionally convergent or conditionally integrable. You know, and you may remember from your analysis class that one of those reasons is that if you take a conditionally convergent sum like this one, you can rearrange the sum, right? So do the sum in a different order, right? So basically it just means you take the terms in the sum and you permute them, okay? And you can rearrange them in a way that you can get any number as a finite number as the limit of that sequence. Or you can rearrange them so that the sequence, the sum, the partial sums diverge to either plus or minus infinity, or don't converge but not necessarily by diverging. So there's all kinds of things that are problematic about conditional integrals and conditional sums. So that's one reason why you want to restrict to absolutely integrable and absolutely summable things, okay? All right, so our definition of the Riemann integral is designed so that we're talking about absolute integrability. Okay. Okay, so let's look at an example to sort of illustrate what's going on here. Okay, so let's take this function f of x on the interval from 0 to 1, which is open at 0, and so f of x is a continuous function on that interval, okay, but it's not bounded. Goes to infinity there. Okay. And let's see if this is Riemann integrable by our definition. Okay. So for r in 0, 1, we have the integral from r to 1 of x to the minus 1/2 dx. Okay, so that integral is one that you can do, and it's 2 x to the 1/2 from 1 to r. Okay, and so that's going to be 2 minus 2 root r. Okay, and so the point is that the limit as r goes decreases to 0 of integral from r to 1 x to the minus 1/2 dx is equal to 2, which is perfectly fine. And so therefore this function f, although it's not bounded, is Riemann integrable. Okay. Okay, so that's sort of illustrates very quickly, and it's not really the best way to define the Riemann integral. You know, so just to give you some idea about why this is maybe not the best thing to do, is there's no reason why you couldn't think of this function as being defined on the closed interval 0, 1, and, you know, taking its value to be 0 there. But then according to our definition, this doesn't work because on compact intervals, you know, our definition of the Riemann integral requires functions to be bounded, and it seems kind of artificial. And there's ways of doing that, and the way you do that is you kind of truncate. You don't just do the limits as a compact interval grows to fill out your non-compact interval, but you also sort of truncate off the values of the function. And then take, you know, to some m, and then you take to allow m to become unbounded. All right, so there's different ways of doing this that are better than what I've described here, but I don't care, because eventually I'm going to replace the integral with a different one, which is better in every way than any definition of the typical definition of the Riemann integral. Okay. All right, good. So that's Riemann integral. And now, as I said, the problem with the Riemann integral is that it admits this kind of function that I talked about last time, which is a function that is not Riemann integrable, but which is a limit of a sequence of Riemann integrable functions. And the function was a silly function. It's this function which on the interval 0, 1 is 1 at every rational value and 0 at every irrational value. Okay, so that's not a function that's of great interest. But the phenomenon there that is of some interest is this fact that that function is a fairly benign pointwise limit of Riemann integrable functions, but it itself is not Riemann integrable. Okay. And so now we want to come up with a new definition of integral that repairs that in some way, and that definition will be as I've already said, is what's called the Lebesgue integral. And the Lebesgue integral is constructed one way to, there's many intuitive explanations about what the Lebesgue integral is. One of them is that it overcomes the problems of the Riemann integral by enlarging the ways that you approximate a function, right? Because last time when we constructed the Riemann integral, what we saw is that we approximated our function, you know, by choosing a partition. We approximated our function, let's say, you know, by below, by step functions like this. Okay. And it's the fact that step functions are defined as being constant on intervals that causes the problem there. And what you want to do is you want to come up with a class of functions which is constant, not on intervals, but on more interesting kinds of sets. Okay, so we want to enlarge the class of approximating functions from step functions to functions that are piecewise constant in some way, this really is, kind of the normal definition of piecewise constant, and the piecewise here refers to the intervals. Okay, so that's why I put piecewise constant in quotes there, because it's not, it's in conflict with the sort of standard terminology, that are piecewise constant on by being constant on sets more general than intervals. Is the idea. Okay, and so the first step in doing that is to, come up with the replacements for intervals. Okay, so the sets are what we will call measurable sets. Okay, and so the point is that the resolution of this takes one into talking about measure theory, and so this is now so the measure theory we're going to talk about is what's called the Lebesgue measure. Okay, so the Lebesgue measure was sort of brought to us by Henri Lebesgue, French mathematician, in the early part of the 20th century, and it's one of the cornerstones of modern mathematics. Okay, because the definition of the Lebesgue integral and the property of the Lebesgue integral allow you to do rigorously a lot of things that would be difficult without it. Okay, so I think what I'll do is I will stop there, and next time what we'll do in one lecture is talk about Lebesgue measure. Okay.